In this video, we're going to examine how to set up and solve systems of coupled differential equations. And we're going to do this by example. In the first of the two examples, I'm going to discuss a system that has two components, so two tanks. We have tank 1 and tank 2. And it starts off, this type of problem, in tank 1, you have pure water, 100 gallons of pure water. And in tank 2, you have water, but you have some dissolved substance. In this case, we'll use fertilizer, but it could just as well be salt, sugar, whatever. And the two tanks are connected such that there's flow between the two tanks. So from one tank to the other. In this case, we're going to have 2 gallons per minute going from tank 2 to tank 1 and 2 gallons per minute from tank 1 to tank 2. We can assume that the tanks are well stirred, so there's a uniform distribution inside the tank of whatever's dissolved. And what we know is we know we have some idea of the rate of change of, in this case, fertilizer in each tank, and that is proportional to the amount of dissolved fertilizer in the other tank. Okay, so what we don't have and what we need to solve for is the function that describes the amount of fertilizer in each tank. So y1, we'll use y as our variable. Y1 is the amount of fertilizer in tank 1, and y2 is the amount of fertilizer in tank 2. Okay, so let's set up the problem. I'm just going to move that out of the way. So let's draw a picture here for what we currently have. Okay, so we have a tank. I'll just draw it. This is going to be my version of a tank here. Okay, here is tank 1. Here is tank 2. This one is 100 gallons, and tank 2 is also 100 gallons. Okay, and what we have between them is we have flow of 2 gallons per minute in one direction, and we also have flow in the opposite direction of 2 gallons per minute. Okay, and what do we want to know? Well, we want to know, we're going to have a curve basically. This is what we expect. We're going to have, so it starts off here in tank 2, we have 150 pounds of fertilizer. So if this is y, okay, this is going to be y2 at t. Here, it's going to start off at 150 pounds. Okay, and then what we expect is that tank 1 is going to gradually get more fertilizer. So it's going to start off at 0, and it's going to approach steady state. So here, somewhere in the middle, we expect half of 150. It's going to be about 75. Now, this is just to give you an idea, okay, and this is going to be y1 at t, this is time, and this is y at t. This is the amount of fertilizer in each tank. Okay, so what do we know? We know rates of change, okay, and so what we know, we're going to set up a model here. So here's our model, and this is what we know. We know that y1, okay, dy1 by dt, the rate of change of y is given by the inflow rate, okay, and we're talking about pounds. See, the units, we should write this down. This is in pounds per minute, okay, because we're dealing with pounds of fertilizer, and y1 of t, let's say, is the amount of, it's in pounds per minute, okay, minus the outflow rate. Okay, and the same thing is true. So this is tank 1 and tank 2. The rate of change of fertilizer in tank 2 is also the inflow rate minus the outflow rate. Now, we got to look at our units. Okay, again, this is in pounds per minute. Okay, so what do we know? What do we know? We know. Okay, let's start with equation number 1, and we're gonna figure out what is happening here. Okay, first thing we know. Okay, let me rewrite equation 1. So dy1 by dt. Now, what is the inflow rate to y1? We've got 2 gallons per minute, so we're going to say 2. And here we're going to use our units, 2 gallons per minute. But remember, y1, dy1 by dt is in pounds per minute. So we need to convert this. So we need to have something over gal to cancel the gal, and we need something that has pounds. Okay? Now, how many gallons are in the tank? Well, there are 100 gallons, okay, in the tank. How many pounds, okay, are coming in from tank 2 to tank 1? Well, that depends on the amount of pounds that are in tank 2. So it's y2 at t. Okay? So this now has the correct units. You have gallons, which cancel with gallons, and you have pounds per minute. So that's our inflow rate. Right? The amount coming in depends on the amount that's in the other tank. And y2 at t is how much is in the other tank at time t. What's the outflow rate? The outflow rate out of tank 1 into tank 2. All right, we've got 2 gallons per minute. So we got 2 gallons per minute, right? Now we got to do the same thing. We need something that will cancel the gallons and have pounds at the top. Well, how many gallons do we have in tank 1? Well, we have 100 gallons. Okay, and how many pounds of fertilizer are in tank 1? Well, that is y1 at t. Okay, and you can see that gallons cancel, and we have pounds per minute for equation 1. So the units check out on the left-hand side on equation 1 and the right-hand side. Okay, let's take a look. The same thing can be done for equation number 2. So dy2 by dt, it's exactly the same setup. We've got 2 gallons per minute coming into tank 2, okay? And what is the amount? We gotta again go pounds per gallon. How many gallons are in tank 1? There's 100 gallons from tank 1. And how many? What is the amount? You can look at this as a concentration. So it's y1 of t divided by 100 gallons, right? Coming in to tank 2. You see, tank 1 has y1 of t amount of salt. Tank 2 has y2 of t amount of salt dissolved in 100 gallons. So this is the same thing. We have y1 of t dissolved in 100 gallons coming in. And again, you're going to have pounds per minute coming in to tank 2. And what's the outflow rate from tank 2? Again, we have 2 gallons per minute of flow. We need to cancel out the gallons, and we want pounds per gallon. How many gallons? Okay, this is outflow rate from tank 2. How many gallons are in tank 2? Well, there's 100 gallons in tank 2. Okay, and how many pounds of dissolved fertilizer? Well, y2. Okay, so these two equations, we've now set up the model. I'm just going to put it in simplified form here. I'm going to remove all the units here. So dy1 by dt. So what we have is 2 over 100. So we have 0.02 y2 t, okay, minus 0.02 y1 of t. That's equation number 1. Equation number 2 is exactly the same here, except that we have y2 in the opposite position. What I should do? Well, I want to line them up nicely. So I'm going to put the 0.2 y2 here. So I'm going to put negative 0.02 y2 of t plus 0.02 y1 of t. Okay. Actually, if we want to have, I should flip that around. Let me flip this around. So I'm going to go negative 0.02 y1 t plus 0.02 y2 t. And this one's going to be the opposite. It's going to be 0.02 y1 of t minus 0.02 y2 of t. Now, I'm going to do that for a reason. And let me, because I want to put these two equations. Usually when you have two equations, two unknowns. So what are the equations? Well, we know y1, or we know dy1 by dt. We know dy2 by dt in terms of y1 and y2. We know those. What we don't know is y1 and y2. Okay. Now, because we don't know, we have two equations, two unknowns. We can solve using matrix methods. So if we put this into matrix form, what we have is we have y1 prime of t, y2 prime of t, okay, is equal to, okay, and I can, let me pull this 0.0 to make that 2 out of 100. Let me do that. Let's go here. So that's like 1 out of 50, right, is 2 out of 100. And what I have is I have negative 1 and 1, and then 1, and then negative 1. And what I have here is y1 of t, y2 of t. Okay? So I have an equation that looks like this. This is 50, by the way. Okay. So if you step back and you look at this, what we have here is we have y prime is equal to, okay, there's a constant here, but I'm going to lump this into 1 here. This is some matrix, right, times y. Okay? I could, if you want, if that bothers you that there's a constant, we can very simply just put negative 0.02, 0.02, 0.02, 2, and then y1, y2, like that. Okay? So what we have is we have an equation that looks like this. Okay? Now, when we have an equation that looks like this, so this is our equation. This is a differential equation right here, okay, in matrix form. Okay? And the way that we solve these types of the equation is we assume the form of the solution. And then we see what needs to be true to make it a solution. So what we're going to assume is that y is equal to x. Now this is just a vector. This is a constant. This is a constant vector. And then e to the lambda t. And this guy right here, these are the eigenvalues. And this whole thing is an eigenvector. Okay, so this is why we studied eigenvalues and eigenvectors in the math course. Okay, so let's take this assumed form of the solution and plug it in. So this is my equation. This is my assumed form of the solution. And I want to see what happens. Okay, so let's sub in y equals x e to the lambda t. Okay, so let's take, so what is, so this is d by d, d by dt, okay? And then it's of y, no, what's y? Y is, let me put that in over here. For some reason my, okay, let's go back to here and see what, okay. So it becomes, now what's y? Y is x e to the lambda t, okay, equals a x e to the lambda t. Okay, well, what is d by dt? Now, x is a constant, so we can pull that out. This becomes d by dt of e to the lambda t. Okay, and that equals a x e to the lambda t. Well, what's the derivative of e to the at? Well, it's just lambda e to the at. So this becomes x lambda e to the lambda t equals a x e to the lambda t. Now, these guys cancel each other out. You can divide both sides by e to the lambda t. So what we end up with is ax equals, here, let me just reverse. Where have we seen this before? If you remember, this was the main equation for the eigenvalues and eigenvectors. Okay, so if we want to solve this, what do? Well, we take everything on the right hand side, bring it over to the left. A minus I lambda times x equals 0. Okay, and if you remember from the eigenvalues and eigenvectors, we'll make this a fancy a, x equals 0. Now, we don't care, like we want x to not be 0, right? So if we want x to not be 0, how would we solve this? Well, first off, how would you solve it? Well, you need a inverse, right? So we say we multiply both sides by this fancy a inverse. Okay, I'm doing whatever I do to the left, I'm doing to the right. Well, a inverse times 0 is still 0, okay? So if a inverse times a times x, that'll equal 0. So if a inverse exists, okay, then you just have x equals 0, okay? That's if there exists a inverse. That's what we're saying. Then x equals 0. This is not interesting. That means there's no eigenvector. Okay? So we don't want a inverse. So we don't want a inverse to exist. Okay? So how do you make a inverse not exist? Well, what is a inverse? A inverse is 1 over the determinant of A times some matrix. We don't care. Whatever it is, doesn't matter. So for A inverse to not exist, right? So that x is not 0, right? So we get an interesting, right? Something that's non-zero. interesting, we'll call it eigenvector. Okay? Then the determinant of A must be 0. Determinant of this fancy A. If it's 0, then A inverse doesn't exist because you're going to have a divide by 0. 1 over 0, right, is, it does not exist. Okay? So we want this det A to equal 0. So in addition to these equations, we got 1 and 2. This is the assumed form of the solution. We also have the condition. So what's A? A is this fancy, is our original A minus I lambda. Remember, that was your A. So it's A minus I is just the identity matrix, lambda equals 0. This is the other thing that must be true. And if you recall from solving eigenvalues and eigenvectors, we used equation number 3 to get the eigenvalues, and then we subbed those eigenvalues in, and we solved for equation number 2. Let me renumber these. This we'll call 3, and then we'll call this 4. How's that? Okay, this is going to be 4. All right, so we used equation 4 to get the eigenvalues, and then sub them into equation 3 to get the eigenvectors, which is x. X is our eigenvectors, and those eigenvectors go into equation number 2 now. Okay, so you got your eigenvectors and the corresponding, you're going to get, actually, what am I saying here? We're going to get the eigenvalues, sub them in, and then we're going to sub them into our equation, okay, to get our y. Okay, so let's keep going. So what do we have? What we need, first step, is find the eigenvalues. Okay, so let's do that. So find, let me zoom in and put this in a nice, okay. All right, so the first thing we got to do is use equation 4 to find the eigenvalues. Find the eigenvalues. Okay, so using number 4. All right, so we need the determinant of A minus I lambda. Well, what is A minus I lambda? Well, what's A? A is this guy right here. There's A. So A minus lambda is just put the lambdas across the diagonal. So negative 0.02 minus lambda. So the A minus, so determinant A minus I lambda is, and these straight lines are our determinant. All right, so it's negative 0.02 minus lambda, negative 0.02 minus lambda, and then we had the 0.02 here, 0.02 here, okay? And we want it to equal 0, right? Because we do not want, we don't want A inverse to exist. So the determinant is down products minus up products, which is basically, okay, we pull the negative out from both of these. That becomes positive 0.2 plus lambda squared, right, minus 0.02 squared. Okay, and so what do we get? 0.02 or equals 0. So equals 0. So what we have is okay, this must be equal to 0, so I'll just leave it like that. So we have 0.02 times 0.02 is 0.02 squared, plus 0.02 times lambda plus 0.02 times lambda is 0.04 lambda plus lambda squared equals, I'm going to bring this 0.02 to the other side, and these two can cancel with each other. And again, it's going to equal 0. So what we have is lambda and then 0.04 plus lambda equals 0. And to equal 0, either for this expression, either this lambda is 0 or this lambda is negative 0.04. So the eigenvalues are their lambda equals 0 and lambda equals negative 0.04. Okay, so these are the eigenvalues. Now, what we need to do is we need to take these eigenvalues and put them, okay, we need to get the eigenvectors. So what do we need to do? We need to take them and put them into equation number 3, okay? So we're going to find the eigenvectors. And the eigenvectors, we're solving for this constant x. That's what we're looking for there, okay? All right, so now we need the eigenvectors. Okay, we're going to use lambda equals, okay, we'll start with lambda equals 0, okay, and what we need to do, we need to put it into equation number 3, which is a minus I lambda times x equals 0. So a minus I lambda with the lambda equals 0 is just a. So the equation is, we're going to have 0, negative 0.02, 0.02, 0.02, negative 0.02, okay, and times x. This is the column. This is a column vector, so we'll call it x and y. You can say x1, x2. It's the same idea. Equals 0, 0. Okay, and what we can do is we can pull out the. This is 0.02 is 2 out of 100, which is 1 over 50, right? So I can leave it here. Why don't I leave it as 2 over 100? And then this becomes negative 1, 1, 1, negative 1. And you can see that the two rows here are the same. So if you can put it into row reduced echelon form, or you can add row 1 to row 2. And basically what that does is that gives you see, 2 over 100. If you add you say row 2 equals row 1 plus row 2, you get negative 1, 1, and then 0, 0, right? And then x, y, and here we have zeros. Okay, so what this means, now 2 over 100, you can multiply both sides by 100 over 2. See, look, what we have is we have, well, we can multiply both sides of this equation by 100 over 2. So really, we don't even care about those two. What we have is negative x plus y equals 0, right? That's what we have. Actually, if you do this, you could say 2 out of, let's be exact, right? And then I multiply both sides by 100 over 2. Okay, and they cancel, and then this becomes, it's still 0. So what I have is that x equals y. So my first eigenvector, the eigenvector, well, the x, okay? So x, I don't know if I want to go like this, is equal to, literally it's just any value times 1 and 1. X and y are the same. Okay, so we can say this is my eigenvector, and what is it? What does it look like? Well, it looks like here's x and here's y. This x, I can give it. I should use a different. I can use it. This is just the scaling, because any vector that goes along this line is an eigenvector. Okay, so if I use 1, 1, then okay, that's one vector. There's other vectors like that. So I can put some value here. I can just say a. A is just the I'm scaling that vector. Okay, or I can just use 1, 1. Okay, all right. So that is my x. Okay, when this is for when lambda equals 0. Same as we did before, we got to do the other eigenvalues. So we need to check for when lambda equals negative 0.04. Okay, and how does that change the equation a minus I lambda? Well, a was, let me put that in here. Okay, it's negative 0.02. Okay, minus, so that's a plus 0.04. We have 0.02, 0.02, and then negative 0.02 plus 0.04. Okay, that's a minus I lambda. Okay, so that's what we have up here, times x, right, equals 0. Now, we said we want to take the determinant. We need to do the determinant of a minus I lambda. So that was the equation, but we want to take the determinant. So I'm just going to write it right here. Okay, we're going to do this determinant equals 0 for a inverse to not exist. So this is just, if you look at this, okay. Oh, wait a minute. I apologize. Let me take a step back here. This is ax equals 0. We're trying to solve for x. We already did the determinant. All right. So what do we have? We have, this is ax equals 0. So we have 0.02, 0.02, 0.02, 0.02 times x is the x and y. Okay, this is a vector, right? Equals 0. X and y are just points now. And so if we pull this out, if we pull out 2 out of 100, what we have is 1, 1, 1, 1, x, y equals 0, 0. Okay, and if you do row 2 equals row 2 minus row 1, then this becomes 0, 0. And what we have is x plus y times 2 over 100 equals 0. And you can cancel that out because I'm going to multiply both sides. 2, this is going to cancel. And we get x equals negative y. Okay. So this this vector here becomes, this x vector becomes, here it looks like this. It becomes, so the x vector is x and negative x, or we could quite literally, whatever value x is can be anything. So I can just, let me say b times 1, negative 1. Okay, so that's what it is. Literally what it is, the eigenvector. If this is x and this is y, we have x is 1 and y is negative 1. So here's 1, y is negative 1. We have anything that's along this axis. Okay, could be any length, right? Can go this way, can go this way. Okay, so b can be a positive or a negative value. So this is the eigenvector. This is the other eigenvector. Okay, so what do we have? We have, let's take a step back. We have, so we solved for x. Okay, we solved for, let me go back here. Okay, we solved for our eigenvalues. Okay, we solved for x. Okay, those vectors, and we have we had an assumed form of the solution. Let's go back to this guy right here. This is the assumed form of the solution. Okay, y is x times e to the lambda t. We've got the lambdas, we've got lambdas, and we've got x's for each of them. We got the eigenvalues and the eigenvectors. Okay, so we have the two solutions. Let's go back. Okay, we've got the eigenvalues and the eigenvectors. So let me go in. So the solution. Okay, so we said that y is x e to the lambda t. And we have two particular solutions. We have y1 is equal to, now x was 1, 1, okay, times here. I'm using a and b. So this is going to be a, 1, 1, e to the lambda equals 0, right, in the first case. So this becomes just a 1, oops, not 1, over 1, a 1, 1. And y2, this is a t, y2 is equal to b 1, negative 1, e, now lambda was negative 0.04, okay, and times t. Okay, so these are particular solutions. Okay, so these are the two particular solutions. Now, what do we know? What we know is that the general, so we how many, let's go back here. We have two particular solutions, okay? And this is a vector space, okay? We have two variables, two unknowns. So we have two space, we're in two space. So there are going to be two particular solutions, and the general solution, okay, is the scaled sum, the linear combinations of the two particular solutions. So the general solution is, so y of t equals c1 y1 of t, that's the first particular solution, plus c2 y2 of t. Now a and b are constant, so I can group them into c1 and c2, no problem. So y of t is equal to c1 1 1 plus c2 e to the negative 0.04 t. And that's it. That is the general solution. Okay. So now what do we know? We need to solve for C1 and C2. Okay. So from the general solution, you can get the particular solution to your problem using the initial values. Okay. So the particular solution comes from, right, requires the initial conditions. Initial conditions. Okay, so that is what we need to figure out. Now, this y of t, let me write this out a little. Oh, I forgot something here. I'm missing something because y2 also has that vector. Okay, it's plus 1, negative 1, right? Let me slide this over a little bit. Okay. Quite literally, what this means is y1, y2 of t. If I put these like that, okay, that is what our system of equations looks like. So what we have is we have y1 of t equals c1 plus c2 e to the negative 0.04 t, okay? And then y2 of t from this equation, okay, is c1 minus c2 e to the negative 0.04 t, okay? And what we need to do is we need to figure out, based on the initial conditions, we need to figure out what is c1 and c2. So what we know, y1 at time 0 has no dissolved. Okay, we have no fertilizer in tank 1. y2 at 0 is 150. Okay, and so from this we can solve for c1 and c2. So let's take this, sub in there, and get, okay, so y1 at 0 is 0 equals c1 plus c2. What is, when t is 0, it's just like that. and y2 at 0 is 150. It is equal to c1 minus c2. So we can solve for that. Here we're saying that c1 equals negative c2. Okay, from this is equation 1, this is equation 2. So if we sub from equation 1 to equation 2 becomes c1, right, plus c1 equals 150. So c1 equals 150 over 2, which is 75, which means that c2 equals negative 75. So now we know our system of equations. We know C1 and C2. We can sub them back into our main system of equations. Here is y1 of t, y2 of t. We'll put it in matrix form. Equals 75, 1, 1. And then C2 is minus 75, 1, and negative 1. Then e to the negative 0.04t. This becomes our the solution to our differential equation. So this right here, let me just collect it and move it over. Just move it down here. This is the solution. This is what we were looking for the whole time. I don't know what just happened there, but I'll get rid of it. Oops. Let me see if I can undo. It's got to be an undo button here. There we go. Okay. Let's do. Okay. All right. So this is the solution that we've been looking for the whole time. And now we can answer the original problem. The original problem was at what time, when, okay, what time is y1 equal to half of y2, okay? When will y1 be 1/2 of y2? We have this 2, right? So when, okay, this is y1, this is y2. At some point in time, okay? Now, if there's 150, I'm thinking 150, okay? So y2 would be at 100 and y1 would be at 50, but we don't have to guess, because all we have to do is say take y1. y1 is 75 minus 75, right? E to the negative 0.04t, and when does that equal? Let's say 1/2 here, and then it's 75 plus 75 e to the negative 0.04 t. Okay, so when is y2 or y1 half of y2? And that's what we're looking for here. Something going on with the way my. All right. So what are we going to do? We can pull here, pull the 75 out. So we'll pull 75 right out, make these just 1 and 1. What's 75 divided by 2? Well, we can leave. Actually, we can pull the 75 out of this side as well. So that's a 1. This becomes a 1. We can cancel out the 75. So we have 1 minus e to the negative 0.04 t equals 1 over 2, 1 plus e to the negative 0.04 t. Okay, and we're going to solve for t very shortly. So let's go in here. Let's bring the 2 over here. So I'm going to go multiply both sides by 2. Okay, good. And I'm going to bring this over to this side. So it becomes, or actually, let's bring this over to that side, and this guy over to that side. So we got 2 minus 1 equals 2 plus 1. So that's going to be 3 e to the negative 0.04 t. Okay, And so that is 1 equals 3 e to the negative 0.04t. So that means here, let me reverse it. E to the negative 0.04t equals 1 over 3. Okay, and to solve for this, I need to take the ln of both sides. I'm going to say ln e to the negative 0.04t equals ln of 1 over 3. So this becomes 0.04, negative 0.04t equals, correct. Yeah, because this will be negative 0.04 t ln e is just a 1. Becomes ln of 1 over 3. So that means that t equals negative ln 1 over 3 over 0.04. Okay, which gives me 27.5. And everything was in minutes, right? It was pounds per minute, so the units are minutes. Okay. All right, so let's recap what we did. Okay, and zoom out. Let's go down here. All right, we started off, lots of zooming here. All right. Okay, let's do a recap. We started off with a model. Okay, and that model basically had that the rate of change. Okay, let me use a red pen here. Okay, or maybe we'll use a fancy colored. We'll go with this one. Okay, the rate of change, okay, of the dissolved fertilizer in tank 1 we call y1. Okay, the dy1 by dt, and the rate of change of the dissolved fertilizer in tank 2 is dy2 by dt. And we know something about the rate of change. It's an inflow minus outflow rate on both of them. To make this work, we knew that we were working with pounds per, dy by dt is pounds per minute. Okay, so both sides of the equation need this pounds per minute units. Okay, we know the flow is 2 gallons per minute in either direction. So when we're talking about inflow rate, both of them had 2 gallons per minute. Okay, and in order to convert to pounds per minute, we had to multiply by a pounds per gallon. And where do we get that? Well, we know that there are y1 pounds. Okay, we're talking about now outflow rate from y1. Okay, it has y1 pounds dissolved in 100 gallons going out at 2 gallons per minute. Okay, and so we have y1 pounds in tank 1 dissolved in 100 gallons. The same thing is true for the inflow rate. The inflow rate, there was 2 gallons per minute, okay, to tank 1 coming from tank 2, times the amount of fertilizer that's dissolved in the 100 gallons in that tank. And again, the gallons will cancel out and you'll get pounds per minute, which matches the units on the other side. And the same thing holds true for tank 2, just in the opposite direction. Okay, what did that do? Well, that gave us a system of equations, okay, which we have here, okay, and that's in matrix form, okay. And what we need to do was we need to assume the form of the solution, okay. So we assume that for this, okay, for this differential equation, we're assuming the form of the solution is y equals x, this is a constant vector, times e to the lambda t. Okay, the lambdas are the eigenvalues. This whole thing is the eigenvector. What we need is x, okay, because x times e to the lambda t, that's going to be the entire eigenvector, okay. All right, so what do we do? Well, we need to solve this. So we assume the form of the solution. No, that's equation 2, and we sub it in to equation 1. And what that leads us to, 1 leads to 3, okay? This is basically the same equation. what you get on both sides is a minus I lambda x equals 0. And we know that we do not want x to be 0. Okay, so for x to not be 0, to be something interesting, right? Something other than 0, the 0 vector is useless, right? It's nothing. So for it to not be 0, then A inverse cannot exist. Okay, for A inverse to not exist, we need the determinant of A to be equal to 0. So we get this equation number 4. And we did this before when we studied eigenvalues and eigenvectors. So what we do to solve the equations is we say, okay, look, I need to solve the lambdas using equation 4. Okay, then once I've solved them, I plug them in to equation 3 one at a time. That's what we did. We said, okay, we solve for the eigenvalues by taking the determinant of A minus I lambda, setting it equal to 0, and we get, because it's a 2 by 2 matrix, we expect 2 eigenvalues. Okay, and for each of the eigenvalues, okay, what we did was we solved for the eigenvector that corresponds to that eigenvalue. Okay, and in this case, we got some constant times 1, 1, and that basically anything that goes on this line, any vector that's on that line. Okay, and for the other one, sorry, this is a little bit bigger than the other stuff, but basically this row and this row are repeats. So this, you can do row 2 minus row 1 equals row 2, and you get 0, 0. Okay, this is literally this just gives us x equals minus y. Okay, for this column vector, and what that means is that you can have any scalar, okay, times 1, negative 1. Okay, and that's basically anything that's along this line, any length. B can even be negative. That's why it can change direction there. Okay, the angle, right? The angle does not change with the x-axis. Okay, that's why it's an eigenvector. Okay, fine. So we've got two eigenvectors that correspond to the two eigenvalues that we got. So we got y1. This is eigenvector number 1 with eigenvalue of 0. This is eigenvector number 2 with eigenvalue negative 0.04. And the general solution, okay, is the scaled sum of the two particular solutions. Okay, and we're in a 2 by 2 space, so the matrix A is 2 by 2. So the dimensions of our vector space is 2. So we expect two particular solutions that we can scale and sum. So we expect two basis vectors, okay? And those two basis vectors can be scaled and summed to give us our solution space. Okay, cool. That's awesome. So we've got these. This is the general solution. We want a particular solution to our problem. So we need to solve for C1 and C2 using initial conditions. And the initial conditions for our problem is that tank 1 had no dissolved, it was pure water, no dissolved fertilizer, and tank 2 had everything, 150 pounds dissolved in 100 gallons. And we use that to solve for C1 and C2, so 75 and negative 75. And we sub them back in, put it back into matrix form. This is our equation. Okay, this is our solution to the differential equation. This will tell us everything we need to know about this coupled system. All right, then what? Then what we did was we said, okay, what was the original problem that we wanted to solve? Well, we wanted to know that's time, and this is the amount of dissolved fertilizer in each. And so we said, well, when will y1 have half of what's in y2? What is this time here when they'll be? And you can kind of see, if you had 150 to start with, 150 means that y1 will have half of y2. But if we work it out, we just set y2 y1 equals 0.5 y2 and just take this equation. What you'll get after you take the ln of both sides, after you solve for t, you get 27.5 minutes. So t0 is 27.5 minutes. So after they've been stirring for 27.5 minutes, you'll have half of the fertilizer in the other tank. All right, I hope you enjoyed this video, and we'll see you next time in math class.